Let's start. I'm very happy to pronounce Tony Pan, who will tell us about mirror symmetry and the Breuil-Mezard Conjecture.
Yeah, thanks a lot for the invitation to come. It's great to be back. I was actually here a couple years ago, and I still have my IS swag from them, which I brought today. So let me just sort of begin by setting some information about modular forms, which will be kind of motivation for this talk. So probably what I'm going to say is known to most of you, but let me say it anyway. So SL2Z acts on the upper half plane, and more generally, we'll be interested in finite index congruent subgroups of SL2Z. So this action is by linear fractional transformation, A, B, C, D, send Z to AZ plus B over CZ plus D. And when I say the space of modular forms of weight K and level gamma, I'm thinking of homomorphic functions from the upper half plane to the complex numbers, such that they transform under this action in some specified way. So f of AZ plus B or CZ plus D is CZ plus D to the K times f of Z. And then I furthermore stipulate some kind of extension to infinity. I say that it's homomorphic at infinity. So let me just say it extends to the boundary of this subgraph plane as well in some way. So this is what I mean by the space of modular forms. And some of our favorite examples of gammas that will come up other than SL2Z will be something that, let's say, gamma naught n. So that's matrices A, B, C, D, where C is 0 mod n. And notice that this in particular includes matrices of the form 1 something 0 1, which act by translation. So functions with the space of functions here consists of functions that are translation invariant. So they have some Fourier expansion. So in this case, you can write your f as a sum of let's say an times q to the n, where q is e to the 2 pi z. So this encompasses some of the standard notation that I'll be using. Something about this definition, which is not really obvious if you're approaching it for the first time, is that first of all, these functions, this space, although a priori is a kind of complex vector space, turns out to have an almost integral basis, and furthermore, there's lots of congruences between such modular forms. So let me just illustrate this through an example. So one of the first modular forms that you write down, that you learn about, is something called the delta function, and its Fourier expansion has the following flavor. So it actually admits a kind of product description like so. So this turns out to be weight 12 and level 1, so let's say SL2Z. And I want to think about this guy mod 11 specifically. So mod 11, this thing is congruent to, I'm going to start writing down the same stuff, but then I'm going to pull out a 1 minus q to the n squared, and then there will be like a 22nd power left, and then the 22nd is 2 times 11. I can absorb that 11 on the inside, so I can write it as 1 minus q to the 11n squared. And it turns out that not mod 11, just this expression down here is the Fourier expansion of another modular form of weight 2 and level gamma naught 11. So I defined for you gamma naught 11 up there. It's things where the lower bottom left entry is congruent to 0 mod 11. So from a kind of like Bayesian statistics point of view, this is a little bit surprising because like these spaces, they're sort of finite dimensional and they're discrete. And then they have these like infinitely many Fourier coefficients. And so the probability that, you know, 2 Fourier coefficients agree is less than 1. And nevertheless, this type of congruence tends to happen a lot. For example, I explained that delta is kind of the smallest, the earliest cup form in some sense. So it wasn't hard to find this example. So that suggests that there's some kind of more representation theoretic structure, or there's some extra structure going on, which turns out to come from representation theory. namely by something called the Eichler-Schmidt relation. If you look at modular forms of weight k and a given level, and you look at the Hecke eigenforms, and here you look at the Hecke eigensystems, they'll be the ones appearing in the group cohomology of SL2Z with coefficients, or sorry, I should put gamma, coefficients in sim k-2 of the standard representation. And this, well, it holds all the complex numbers, it holds with the kind of integral coefficients, and in particular, if you look at this, maybe mod p, will still hold. And what you see there, so you take sim k-2 of the standard representation over fp, and now your group acting is some subgroup of SL2Z, so an infinite group. The action factors through this finite group, SL2FP, and this finite group doesn't have that many different representations. And so although all these representations are kind of irreducible and distinct from each other as k varies in characteristic 0, in characteristic p, they start to collapse amongst themselves a lot. And this collapsing will lead to a lot of coincidences in their kind of Hecke eigensystem. So that's what explains this particular example. And what I'd like to do next is to kind of study this representation theory quantitatively enough so that it becomes completely transparent why this particular example occurred. Any questions? Okay. So in other words, so let's have a sort of review of representation theory. So the irreducible representations, so actually let's make this discussion more generally when G is a reductive group over a field K. And I'm interested in the case where K is characteristic 0 or characteristic P. So in characteristic 0, perhaps the theory is a little more familiar. And in that case, what one finds is that the irreducible representations are in bijection with the weights that are dominant. So I don't know, maybe I'll just draw a picture here to remind. So when G is SL2, this X star T thing is the usual integer lattice. And the dominant stuff is kind of the integers that are non-negative. When G is SL3, then we're looking at the kind of hexagonal lattice, and the lattice vectors in particular cone, let's say this this cone, those are the ones which are dominant. And when G is SP4, then our root system looks like this. And again, it's the stuff in one particular chamber which is dominant. So the lattice vectors in these kinds of blue regions, that's what we're talking about right here. And how this works is that given a particular dominant weight, you can construct something called the Weil module with that highest weight, W for Weil. And that's how this bijection works. So maybe, for example, when G is SL2, then the weight is an integer, a non-negative integer, so some n, and this representation is the action of SL2 on homogeneous polynomials in two variables. So it's x and y. Okay, so that's how this story goes. Now, in characteristic P, the picture looks somewhat different. So let me spell that out. If I were to take representations of G over Fp, then the irreducible ones would be in bijection, actually with the exact same thing, the dominant highest weights, and a particular one goes to something which I'm going to give a different name. I'm going to call it L of lambda, just to kind of emphasize that I think of it as a different thing than this W of lambda. So this Weil module is actually a construction which I could make in any characteristic. Like, it makes perfect sense to put in something of characteristic 0 or characteristic P here. But in characteristic P, it won't be the same as this L of lambda here. So for example, I mean, sometimes it's the same, but for example, in characteristic P, when I take the P file module, it has this submodule. So maybe I should, okay. In characteristic P, it has the submodule, which is polynomials in just x to the P and y to the P. And it's the miracle of characteristic P that although this wouldn't usually be stable under SL2, in characteristic P, it is because the Frobenius is kind of additive.
Is it usually a dual biomodule?
I think I want the actual one, but in characteristic 0 is the same, right?
Yeah.
Okay, so the one way to kind of visualize what these representations look like is to write down their characters. That's something we learned in finite group theory. And for a reductive group, that means we would look at the restriction to the torus, T, and then that would be captured by some sum of weight spaces. And for SL2, the picture will look like this. So if you start writing down the weight spaces for W0, that's just trivial representation. So it's just 0 with multiplicity 1. W of 1 looks like this. W of 2 looks like this. And the picture is kind of just a kind of very uniform pyramid. In characteristic P, when you do this, well, it starts out looking the same at the very beginning. But let's say we're doing P equals 2. So, okay, the trivial and the standard look the same, but then for the symmetric square, it's actually smaller than kind of it looked on that side. So what that means is that in this character table, you have to delete this. So the beginning was the same as over there, but then you delete this piece and then you copy the one above it on these two things on the side. And then once you get to here, you're going to delete this again from that kind of filled in pyramid. And then you encounter two pieces which have the same kind of size as this one, and you're going to copy each of them here. So look like this. And then the pattern continues, so on and so forth. So that's one way to kind of visualize like the difference between the representation theory and characteristic P and characteristic 0 here. Okay, and in fact, you see this thing has a kind of interesting like fractal or maybe like reverse fractal structure. As you zoom out, you see copies of the same thing. So notice that this representation here is really just the Frobenius twist of the standard representation. Meaning it's like, you take the matrices by which you act on the standard representation, just raise the entries to the pth power. So that is something which will dilate the weights by p, kind of how like this pyramid got dilated to this one. And in fact, this structure, this repetitive structure we're seeing is a reflection of something called Steinberg's theorem, which says that all the L of lambdas, all the simple representations here are built from some elemental ones. So let's say built from the ones where lambda is inside something called the fundamental box by taking tensor products and Frobenius twists. So actually, I only need to give you a certain fundamental ones, and then these operations will build the rest of them.
Sorry, I think this is just a trivial terminology question, maybe the same question Professor Zhou already asked. But so is your Weil module given by just parabolically inducing from the Borel directly, or do you want to dualize lambda and then dualize the induced representation? Because I think what you're calling the Weil module is what Janssen calls the dual Weil module, right?
Okay. So what I want is yeah, I want the thing whose quotient is this, but somehow, thank you. Yeah, by the way, this may seem not really that related to the kind of questions we were discussing on that board, but in fact, I'll need this notation later, so that's kind of why. And so what is this fundamental box? So basically, I'm going to start looking at hyperplanes inside this picture where you pair with some simple coroot to be a multiple of P. So this is kind of like P here. And then you're going to create sort of things like this. And also a picture here. And the fundamental box is a fundamental domain cut out by these hyperplanes. So it's For SL3 it would look like this, for SL2 it looks like this, for SP4 it looks like this. So it consists of a finite number of coeds. Now, let's get back to the type of representation theory, which is kind of looks more relevant to the questions about modular forms and congruences. So, namely, the representations of not G, but of something like G of FP. Now, if I look at irreducible ones here, then they turn out to be in bijection with this thing that I call the box. That's why I introduced it. And in fact, all the irreducible representations extend to the algebraic group. So the irreducible representations have the flavor lambda goes to that highest weight representation, but then I restrict it to G of FP. So this thing, I apologize, this kind of lots of notation flying around, but to kind of emphasize that we consider it as a representation of this finite group, we call it f of lambda. Okay, and so you can kind of see, if you believe that the representations should extend to the algebraic group, these are the only ones you could expect to get, because once we look at Steinberg's recipe, the Frobenius twist will do nothing to this subgroup. And so, all these other irreducibles are kind of built by tensoring, the ones you already have from the box, but then, when tensor them, they won't be irreducible anymore. So Steinberg's recipe is sort of telling you this is all you could expect to get in this way, and turns out to account for everything. Okay, so this finite group, it's kind of at the crossroads of the representation theory, reductive groups in characteristic P, but also finite representation theory in characteristic 0. So there's other kinds of natural representations of this group which arise. For example, so let's look at some other representations. So you could, for example, take parabolic inductions. So if you had, let's say, mu and start T, you could view it as a character of the torus FP points, and then inflate it to the Borel, and then induce it up to here. So you can make this induction. Which is, I'm going to abbreviate this R1 identity or one mu, because kind of even more generally than this, you could consider a construction from the linguistic theory. So more generally, there's our W mu, where W is an element of the file group. And mu is again a character like this. And this representation is cut out from the cohomology of some varieties, a little bit difficult to, more involved to define, but more or less some kind of twisted parabolic induction intuitively. And so this thing you usually build in characteristic 0, but you can then reduce it mod P by choosing a lattice and tensoring that lattice with FP. And that's well defined, at least in the growth and group of representations. Okay, so somehow I introduced these representations because they're the ones which are suggested by considerations in characteristic 0. So in fact, let's take this story here and plug it into the example from the beginning. And see how it plays out. Okay, so what we saw here is that this example pertains to, let's say, the homology of SL2Z with coefficients in. Now we have sim 10, which is the thing which we call F10. Sim 10 over F11, so P is 11 right here in this example. So the delta function kind of came from this cohomology group, whereas the other modular form in this board up here came from homology of gamma naught 11 with coefficients in will be like weight 2, so sim 0, so the trivial coefficients. That's f of 0, and by Shapiro that is the same as the homology of SL2Z. with coefficients in the induced induction. It's the induction from the Borel over F11 to the full group. So let's just do the notation that I started writing there, and it's called FR1 and then 0 for trivial character. So this kind of thing begs the question of like, how do these representations, maybe I should put, how do these representations look like when you decompose them in terms of the irreducibles over here? So for example, in general, if you took this kind of R1 mu, this is induced from the Borel, whereas if you want to compare it to this simple, I mean, this is the highest weight representation. So kind of is the universal thing with a vector that's transformed under the Borel by this character. So there's a kind of tautological map like this. And then when you dualize, there's kind of a tautological map the other way. And then when you count dimensions, you realize this is short exact. So at least in the Gaussian group, this thing is exactly the sum of these two irreducible representations. And so in this particular case, this thing has this as a sum. And in fact, it turns out to be the direct sum of this f of 10 plus f of 0. But in any case, the point, which is the upshot is that from this point of view, so this thing is like, and 0. From this point of view, it becomes completely obvious that everything which you see here, all the eigensystems you see here are going to appear here. And so like this example, we said at first, it was a low probability event. Now in retrospect, it's kind of a probably one event. It had to happen just based on representation theoretic considerations. Okay. Any questions? Okay, so if not, then let me proceed. Let's see. So okay, so you may think like, now I understand where all congruences come from. They just come from representation theory. But in fact, that's not the case. So not all congruences arise in this way. So this is maybe the most naive source of congruences. So there's, I'll just give another example due to Elke's. And here the prime is 107. And there's two modular forms. I can't really remember what they are, so I'm going to start writing down a small part of their expression. Actually, one of them is not that complicated. So it's kind of standard Eisenstein series times this delta function from before. It has weight 26, level 1. And then your other modular form is going to have a long expression. Okay, so I'm just going to give up at this point. Whatever it is, it's a thingy with a long expression, and it has weight 82 and level 1. So let's compare this to the representation theory. So this thing having weight 26 is related to the irreducible representation F24, and this thing having weight 82 is related to the irreducible representation F80. But in particular, these are both irreducible and they're not the same thing. So, I mean, there's not a representation theoretic grounds for there to be some kind of congruence between the forms in this weight and this weight. So something more subtle is going on here. And I want to explain what that is. So we'll come back to this later. Okay, so I'm going to describe kind of a conjectural picture. And this conjectural picture is going to try to explain like where all congruences come from. And let me just say, so up till now, the talk is meant to be somewhat of a leisurely stroll where, you know, things were defined and statements were true that were made. And what we're going to do now is board a train where that's going to be less true than before. So it's going to become a little bit vaguer and more pessimistic. So
Things won't be defined, statements will be false.
that's right. Okay, so G will be a reductive group. And then there will be something called the dual group. And really, I think it's interesting enough for our purposes to think about GLN, in which case the dual group is also a GLN. But there will be, I don't know, just list some more examples in case they aren't familiar. So on and so forth. So the idea is that there should be some notion of automorphic form for this more general reductive group G. And previously we had basically been discussing SL2 or GL2, basically SL2. So the idea is that given an automorphic form F for G, we're going to be able to cook up some Galois representation. This is a conjecture. And furthermore, I didn't say everything would be exactly true. So certain technical details will be like maybe simplified or something. But okay, so there will be some associated Galois representation. But the idea of the weight part of Serre's conjecture, which is attempting to classify like what possible congruences can occur, is that the congruences which can occur depend only on the restriction of this Galois representation of Q to QP. So let me put this slightly vague. Okay, let me put this vaguely. So congruences determined by the restriction of rho to Gal QP over QP bar over Q. Okay, so again, the idea is sort of like when we're looking at a Heck eigensystem, we're trying to determine which weights it can come from, maybe more than one weight. So like the weights being kind of information of the K, but also the gamma in this situation.
These fields for G and G check.
Let's say Q, and this is something like QP, but okay, let's not worry too much about it. Okay. So
What kind of automorphic form do you have?
homological, so cohomology, you have the locally symmetric space. Okay, so
So G not is not necessarily split, or
not necessarily, but I mean, the split case is interesting enough, but no, it's not necessarily split. Okay, so when I say determined, however, the determination process is subtle. So I don't know, parentheses, but determination, but this determination is subtle, and it depends on understanding not just like what this is as a representation, but kind of understanding its position in moduli. Its position in the moduli space of representations of this group. So oh, actually, yeah. So so the idea will be that there's this space X, E, G, Hamilton G stack of representations of Gal QP into G hat. Well, it's a thing over ZP. I'm interested in representation with ZP coefficients. It's actually supposed to be a formal thing over ZP, but I'm gonna pretend that it's really over spec ZP. And what I'm saying is that in particular, therefore, there's like, you can look at its special fibers. It's characteristic P points or characteristic P substack. And then there's going to be some kind of, the space looks some way. It's not irreducible. And for each reducible representation of G of FP, I'm going to try to make a thing called the Breuil-Mezard cycle. Okay, so it's some kind of union of irreducible components with multiplicity, something in the top dimension. And it's supposed to control like the possible local Galois representations that come from automorphic forms in weight sigma. So for example, like if you had homology of the symmetric space with coefficients in sigma, then and you took an automorphic form here, a Hecke eigenform, then well, its local Galois representation should land inside this Breuil-Mezard cycle. And kind of the converse would be true as long as you allowed yourself to ramp up the prime to P level. So this is kind of the locus of representations, Galois representations, which you can see from this automorphic weight. And at the same time, it's if you allow to increase the level away from P, then you should see all things this way. Okay, so so what is going on in the, where's that example? Oh, maybe I erased it. Did I erase the thing with like the many E4s and E6s? I did, okay. Okay, well, I'm gonna have to write that thing down again, so. Okay, whatever it was, there was something in weight 26 and something in weight 82. That's basically the only information that's necessary, or that's like we're going to use now. And so we're going to try and understand what the mod P Galois representations look like. So there's a component where kind of on inertia, it looks like cyclotomic character to the 25th and 1, and then some extension, generically at least. So what I'm saying is that when sigma is f of 24, the z of sigma generically looks like parametrizing this type of representation. And so, okay, 24, 25, 26, there's some method to this madness. So this M82, it's going to look like a component where the generic representation is an extension of cyclo to the 81 by trivial, and then with some on inertia with some extension. And so these two look different, but as this extension kind of crawls towards the 0 extension, when it hits 0, it'll be a sum of characters. Cyclo to the 81 and trivial. And similarly, when this thing hits 0, it'll be a sum of characters. And then by the coincidence that 81 plus 25 is 106, which is 107 minus 1, then these two will differ by some central twist. So actually they'll be the same in PGL2. So what I'm saying is that actually this kind of Z sigma and Z sigma and the ZF24 and the ZF80 won't be disjoint, they will intersect at one point. And so if you have a Galois representation which lands at this one point, then it sees a contribution from both of these weights. That's what's going on in the example. So actually this picture was not a good picture because in characteristic P, these irreducible components intersect. And we just saw that happen in one particular example. So that's one possible source of congruences from this point of view, is that your so-called Breuil-Mezard cycles may intersect. And at the intersection points, there's kind of more than one weight which would assign the single thing. Another possible source of congruences is that this thing may itself be complicated. So for example, it may be more than just an irreducible component. So this happens when you take ZF P minus 1. It actually is not irreducible. It has two components for SL2. And the other component is kind of like the ZF0. So that is to say that the geometry of this cycle can become complicated. Actually, for SL2, it doesn't get worse than this. So basically what Serre did was, in this language, was to tell you who these cycles should be. But as the group gets more complicated, we actually don't know what this cycle looks like, what the Z sigmas look like. And well, we basically know they become pretty complicated. Maybe very complicated in the sense that the number of components can grow uncontrollably with the rank. And that's another source of conjectures. And kind of interesting historical aside, the fact that this happens is a kind of weird thing, which is at the source of this epsilon conjecture, which Rivet proved and then led Wiles to the proof of Fermat's theorem. So, right. So, so what I'm trying to say so far is like there's some global motivation to understand like what these Breuil-Mezard cycles look like. But once we are interested in this problem, so I said this was a conjectural picture, and part of the conjecture is the existence of this thing at all. So conjecture. The existence of such a cycle. So we're kind of led to be interested in the purely local question of constructing such a cycle inside the moduli space of local Galois representations. So that's actually what I really want to focus on talking about. And the Breuil-Mezard conjecture is a way to try and pin down who this is, or to give constraints on who this is. And so the idea is like, let's look at this moduli space, not just representation in characteristic P, but kind of the whole thing. So we could also consider representations in characteristic 0. And here I'm lying slightly where I'm pretending this is like a stack over ZP instead of a formal stack over ZP. But it's a good approximation to the truth. So basically, when we look at representations of the Galois group in characteristic 0, we have this tool, p-adic Hodge theory, and it allows us to assign various discrete invariants to representations. For example, if you look at potentially crystalline spelling, you look at potentially crystalline loci, then there's invariants you can assign to it, such as Hodge-Tate weight lambda, which will be, let's say, a dominant co-weight and a dominant weight, and then an inertial type. So some representation of the inertia group, which is like, I have to make some ramified extension for this thing to become crystalline, and I take its decris, and that decris has an action of inertia group. That's what these discrete parameters are. So I can really, they allow me to sort of kind of divide the potentially crystalline locus into infinitely many disjoint pieces. Okay, so the geometry of this Emerton G stack, I mean, it's very different in characteristic 0 from characteristic P. In characteristic P, it has a finite number of irreducible components. In characteristic 0, it has like an infinite number of disjoint connected components, at least on the potentially crystalline stuff. And then it's kind of like a formal thickening of the potentially crystalline stuff. So I don't know, I just mentioned maybe a toy model for this picture is like UP infinity. Around the generic fiber, you see like an infinite union of disjoint points, and then they kind of collapse and onto some kind of bounded space on the special fiber. So anyway, the idea is like this cycle is somehow dictated by representation theory, like it's parameterized by representations of a group. And similarly, this thing has such a property in characteristic 0, namely, for example, if you took an automorphic form in characteristic 0 with coefficients in a particular representation. So from this inertial type tau, I can use, at least like let's say for GLN, the local Langlands correspondence to construct some kind of corresponding thing, which is a representation of G of ZP. Instead of a Galois representation, I get a representation of G of ZP in characteristic 0. And if I feed that representation into here as the coefficients of this this cohomology, then whenever I have an automorphic form F like this, its kind of corresponding Galois representation is supposed to lie inside this thing. That's the kind of statement that Peyre-Koch theory tells us. Okay, so the point here is that like in characteristic 0, there's some process which we understand by Peyre-Koch theory to go from representations of G of Z, actually really G of ZP, to these loci in this stack of Galois representations. And we're searching for a kind of similar or analogous construction in characteristic P. And we're going to try to actually use compatibility with characteristic 0 as the desideratum for such a construction. Okay, so now I'm going to attempt to formulate this Breuil-Mezard conjecture. Oh. Sorry, I should have said, so that previous conjectural picture I mentioned, this kind of not growth of work of Serre, especially focused on the SL2 situation, and Ash Stevens and Breuil-Mezard and Emerton G and G and Kissen. And okay, maybe those are the main players, but also, of course, many other people. And this is a conjecture which grows out of conjectures of Breuil-Mezard for GL2, but also has been like significantly reformulated by Emerton G and G and Kissen. And what it says is that, okay, so I'm looking for a way to go from representations of G of FP to these like cycles on the Emerton G stack in characteristic P. Now, there's something I already know. So this is like conjectural map. And there's something I already know, which is how to go from representations in characteristic 0 of G of, well, okay, at the level of K groups, it doesn't really matter. So let's call this G of ZP, but it's the same as if we did the same thing with G of FP. Okay, so in characteristic 0, I already have this kind of procedure, which I understand from Peyre-Koch theory. Namely, I'm going to take something of the form W of lambda tensor local Langlands correspondent of tau and send it to this kind of potentially crystalline locus x lambda tau. At least its cycle. Okay, so this characteristic 0 story is one which I understand. This is the one I'm trying to make. But I know how to take a representation in characteristic 0 and reduce it mod P, at least in the growth group. So it's some kind of specialization to characteristic P, let's say specialized situation where P is 0. And similarly, at the level of geometry, I can take cycles inside this and specialize them to characteristic P to the special fiber. And I'm going to ask that whatever this map is that's supposed to determine these Breuil-Mezard cycles, I'm going to ask that this diagram commutes. Also, you might wonder, like, do these really span this? So I'm only going to consider the kind of representations which are spanned by this type of thing. So, okay, so I'm going to ask that this diagram commutes. Or more concretely, this is just a free abelian group on all possible, like, irreducible representations sigma. And so giving this kind of map is the same as just picking for each thing a particular cycle here, the Breuil-Mezard cycle. And what I'm asking here is for a certain equation to hold. Namely, if I take this x lambda tau, and then that's on the generic fiber, if I specialize this to characteristic P, then the way it decomposes into these things should kind of match the way that this representation decomposes for all possible lambdas and taus. So let me call this equation like star lambda tau. What is like I have a finite number of possible degrees of freedom, like finite number of choices that I can specify to sigma. and then there's infinitely many lambdas and infinitely many taus, and I want this equation to hold for all of them. So it's this kind of like overdetermined system of equations, you might say. Okay. Any questions? So, so let me say a little bit about like what, just as a remark, because there's like many more equations than, variables, so to speak, then this condition makes this map unique. So the conjectures that exist, you could say that it should also be unique. That's implied by what's already here, because you're specifying many more equations than you are, many more constraints than you have degrees of freedom to begin with. Okay, so some known cases when G is GL2, but like specifically over QP now, in case the question came before, really got to be GL2 over QP. Then it's known by work of Kissen, Askunas, and then also several others who help finish off the remaining cases for small p, and it uses p-adic Langlands for local Langlands. So that's something which is very specific to this particular case. That's why I mentioned it. Like this is p-adic Langlands for this group was known 20 years ago, and then for 20 years people were trying to generalize it, and it still hasn't been generalized to any other group. So it uses something very specific to the situation. Another case which is known, which is GLN over an unramified extension. GLN over some finite extension of QP, but kind of you only allowed to take lambda be some specific. So instead of all possible lambda, we fix this very specific one, and then we ask this equation for all taus, and that's still meaningful because there's still infinitely many constraints, and also they're kind of sufficiently independent that that it still pins down the map uniquely for one thing, and the problem is still non-trivial. So this had been done by G. Kissen. At least at some kind of deformation ring level, and then at a kind of stack level that like what I formulated, Cariani, Emerton, G, and Sabat.
What does 1, 0 mean? Like there should be n integers, right? Lambda is a way to do that.
Oh, sorry, this is 2. Sorry, yeah. Still very specific to 2. Yeah, thank you. Okay, so it turns out that kind of when n is bigger than 2, then the problem is somehow much more complicated. There's some kind of real phase transition when n is bigger than 2. And so there was kind of limited results in the higher rank situation. So there are some results of Le Hung, Levin, and Mora, although the results are kind of complicated to state, so I'm not going to. But like there's many quantifiers which are kind of subtle, but they prove something positive about that case, and they work in a range which we're also going to try. So we're going to study this problem with some constraints, kind of like in the second example, on what we're going to allow for these lambdas and taus. So our situation will be, let's say, GLN over K, which is a finite unramified extension over QP. And morally, our tau is going to be pretty generic. So tau is going to be a representation of the form RW mu. This is a kind of Deligne-Lustig representation, like I was referring to here. W is in the Bao groups, could be anything. Mu is going to be constrained. So a priori mu is lying inside this fundamental alcove. So for SL3, it looks like this, inside this region. But we're going to constrain mu to be not too close to the boundary, not too close to the walls. So that's what we mean by generic. Generic means not too close to the walls. And the walls have side length about p, order of magnitude, and close means closer than n. So kind of p, we're imagining to be bigger, like large relative to n. So, okay, what does the theorem say? So first of all, it says that there exists some construction of these Breuil-Mezard cycles such that this equation, star lambda tau, holds well under the condition that so this mu here in the tau is at least, say, the kind of the size 2n plus the size of lambda from the walls. So you can imagine taking lambda to be very small, like this kind of 1, 0, or maybe for GLN, n, n-1, n-2, blah, blah, blah. That's a very small lambda. In that case, you're basically saying something as long as mu is at least 2n from the walls. Or you could take lambda to be a little larger, but then mu has to be kind of more and more away from the edge. And just for orientation, so there's roughly p to the n degrees of freedom here. There's roughly p to the n sigma, so roughly p to the n variables in our system of equations. And the number of constraints which we're satisfying is like the square of that, so p to the 2n. So although you're not verifying like the infinitely many conditions asked by the Breuil-Mezard conjecture, you're verifying like a lot more than the number of variables. And so this kind of thing wouldn't be happening out of coincidence. And therefore, it's maybe not surprising that, that there's already some uniqueness which one gets here. So let's say if sigma, it's an irreducible representation, let's call it like f of kappa, where kappa is at least 6n from the walls. This is not a very optimized constant, but let's say, okay, for concreteness, if it's at least 6n from the walls, then if conjecture is actually true, then, well, in particular, then there's these like true Breuil-Mezard cycles. So whatever the true things are, they have to agree with the things that we've constructed. And again, that's just because like there's so many equations, constraints satisfied by our cycles that the solution is already unique. So if you're worried about like, well, I don't want to feed these fake cycles into the weight part of Serre's conjecture because maybe they're not the right thing. If there is something correct, then it has to be that thing. And just make the remark that the kind of proofs here, they're kind of completely local and group theoretic. Unlike, well, I guess unlike this kind of more general method of G and Kissen and these guys, which depends on kind of global automorphic input. This stuff is completely local, could work for the exceptional groups. And let me say like sort of separate, completely separate from earlier approaches. Okay. Any questions?
So what is kappa?
Kappa is, yeah, okay, good. Okay, so the Serre weights are like stuff in the fundamental box, which for SL3 is the union of these two. So in principle, kappa could be anything inside this box, but we're asking it to be not too close to the walls. So maybe it's like allow it to be like here. But a priori, kappa is inside the fundamental box.
So what is kappa?
It's the irreducible representation with highest weight.
Ah, okay, sorry.
Yeah, so there's a lot of notation here. So, the last few minutes, let me just try and say something about like what is this kind of new outlook on at least on the construction of the cycles. Maybe not like I have time to go into the proofs of anything, but it is actually based on a kind of old analogy. So let me say, so what is our fantasy here? So we have the p-adic numbers, and it's kind of old intuition that these are analogous to a surface, a topological surface. And then our Emerton G stack would be the moduli space of kind of local systems on this QP. So it should be analogous to the moduli space of local systems on a surface. And that's a thing which actually has a symplectic structure. So whatever that moduli space is, it has a natural symplectic structure. And the reason it's not complicated, it's just like the tangent spaces to such an object would be things that we call H1 QP row, add row. And then when your kind of underlying space has a two-dimensional Poincare duality, then this requires a symplectic pairing. So that's the basis for this this thing here. And then really we're interested in these like potentially crystalline loci. And who are those? Their tangent spaces are H1Fs. So whatever this means, the intuition is that it's a kind of Lagrangian condition here. So that, in other words, kind of the topological version of the problem we're studying is like, we're trying to make some construction which inputs, I don't know, some representation theoretic data about group G and outputs some kind of cycle theoretic data on the space for G check, and in particular outputs like Lagrangians. And so we're motivated to ask, like, is there some story topology where you have like Lagrangians inside a symplectic space and you can prescribe them using some kind of dual data? And in fact, there is such a story. So, so before we were on a train, and now the train has arrived at the airport and we're getting onto an airplane. So whatever level of vagueness and falseness occurred earlier, it's about to be much, much worse. So, okay, so there is such a story. And what is that? How does it go? So I have a symplectic manifold. I make something called a Lucaya category. It's something built kind of out of Lagrangians inside my symplectic space. And then I conjecture, or Kontsevich conjectures, that it's derived equivalent to coherent sheaves on some algebraic thing, some kind of mirror variety. And so here is the kind of duality which lets me specify Lagrangians using some kind of dual input. So basically my hope is to make this story, but like on this column. And that hope quickly gets dashed because we realize like, oh, unfortunately, there's no such symplectic structure here, therefore no Lagrangian structure on these guys. So that doesn't look good. But maybe the thing which this is probably not an old, it's probably not a new fantasy, but maybe what's new is that we just refuse to give up on it. So. Yeah, I'll just draw a picture of like what ends up being the reality. So we have this kind of cycles on the crystalline, potentially crystalline loci of the Emerton G stack, and then we want to start out with like representations of the dual group, characteristic P, and we somehow want to go from here to here, but there seems to be some kind of impassable like C in between, and then C, there's these like little things poking out, which we don't really want to get into these waters. And so we somehow can't move forward, so we're just going to move sideways instead. So this is some kind of a priori mysterious space of Galois representations, but there's a way to take this, again, a priori abstract notion of Galois representations and translate it into more linear algebraic data. And that's what's done by p-adic quantity theory. So there's a thing. And for me, this is something kind of scary. So my instinct is to run away from it. But fortunately, somebody else has explained how to do this stuff. So there's, we're using a particular theory of Breuil-Kissin modules, and it's further developed by Bao Le Hung, Levin, and Mora. And so, okay, we take this space and we write down actual charts with concrete variables and equations. We get to something algebraic, And the hope is that this is a space which has been studied and we can use something we've already proved about it. But that hope turned out to be a little too optimistic. But we say, okay, well, the equations are not that far from being something which is already studied. So let's imagine this family, we can deform it in one parameter to get to something which significantly already has another name. So that name is affine Springer fiber. And okay, so somehow there's a process of deforming epsilon to go from here to here. And significantly, this thing is in the sandy beaches of symplectic geometry at this point. So this thing is already Lagrangian inside some kind of symplectic thingy. And now we can really use this fantasy that we had here. So we on these sandy beaches, and someone has built a bridge, and that someone is Resnikovnikov, Bushida, Alvarez, McGreen, and Yoon. And so we cross this bridge, and we end up, while we were up here on some kind of land, built out of the dual group, we've landed in the land of the group G. So we've crossed some kind of duality at this point. And we can use this kind of almost a mirror symmetry and interpret this thing in terms of coherent sheaves on the flag already for G with some decorations. And we use some kind of localization to go from here to here. So let me actually at this point, I think I'm about over time. So make a long story short, just say like with some kind of localization theory, we can transform representations into coherent sheaves and cross the bridge and come back to the left and get what we wanted. And that's the construction of the cycles. So, okay, apologize for going over. Let me stop there. Thanks for your attention.
Any questions? Sorry, can you say more about what the epsilon thing is?
Yeah, so this is like monodromy condition in Breuil-Mezard modules. Breuil-Mezard modules. Okay, so this is monodromy condition. And
sorry, this is the condition that the connection has log poles at those points.
yes, and so we don't like that because just from a very naive perspective of there's no theorems that we can find that apply to this space. And we like this space because this space is studied by geometric representation theorists. So because there's some equation. Let's think of it as 0 equals something plus the d log. We don't like this d log, so we're just going to put epsilon in front of it and think of this. Think of it deforming an epsilon. Think of this as the fiber when epsilon is 1, and think of this as the fiber when epsilon is 0, so it's gone, so we're happy. And then try to show that as you degenerate epsilon, that the geometry of this top-to-top group remains nice or kind of deforms in a nice way. And it makes sense. So this kind of affine Springer fiber is a local analog of a Higgs bundle. This thing is like a local analog of moduli of connections. And so we think of this family as lambda connections. It's epsilon connections in my notation. So it's like the family that interpolates between the notion of connection and the notion of Higgs bundle.
So have you forgotten about the Frobenius when you start talking about Y gamma?
That's right, yeah. Somehow you can, sort of like the Grassmannian is a model for Stukas, or somehow the Frobenius it disappears in this volcano.
If assume some categorical local alignment, does it procedure just taking the support?
The conjectural one. So yeah. So I guess. So maybe to say who is this Breuil-Mezard cycle supposed to be conjecturally? Conjecturally, there's some kind of categorical local alignments which would be, let's say, include the data of a fully faithful functor from representations of G of QP with FP coefficients to coherent sheaves on this M2G stack. And conjecturally, the Z sigma should be support of, let's call this like LL, support of the local length, of course. Z sigma should be the support of local lengths of the compact induction of sigma from G of ZP to G of QP. Although, even if you had this functor, you would have to prove something, of course, about where it sends the types for it to actually work out with the Breuil-Mezard conjecture.
So what is the significance of the fact that you are considering the topological Chow group everywhere instead of just the usual Chow group?
There's only one Chow group. I mean, there's no.
You mean
Oh, sorry. This is top degree.
Oh,
Yeah, I see your point. Okay, top degree, top dimension. No.
Sorry, did the multiplicities of these cycles have any Galois theoretic meaning?
So yeah, it's a good. So we don't know how to assign some kind of like moduli theoretic meaning. So what the theorem shows is that the multiplicities of these, at least when the theorem applies, so sigma is generic or something, it shows that the question like what is multiplicity has the same answer as some like purely symplectic question or some purely geometric rotation theory question, which we also don't know the answer to. But yeah, so I think it's interesting, like some problems which we have no idea where like assign some kind of moduli theoretic meaning to this, which has the right multiplicities, or assign something which is not just at the level of the Chow group. Those are interesting problems which I think we don't know the answer to.
Can you say something more about what you mean by localization?
Yes. So when people talk about localization in the context, in this kind of context, they're usually referring to something like valence and Bernstein localizations. When I have representations of a Lie algebra, I can localize it to D modules on the flat grid. I mean, there's a question of like how well that works in characteristic P, but it turns out at least at the derived level, it works well. So this, and then you have to try to make the ends match on both sides. So in characteristic P, actually, not all three modules, but the ones with nilpool and P curvature are equivalent to coherent sheaves on the cotangent bundle. And morally, there's some Frobenius twist, which doesn't really matter for the kind of computations we're doing. But this is something, a principle called Cartier descent. And this whole story was worked out by, so composition maybe of these was worked out by Vesnikov, Mirkovic, Ruminin. So they kind of explain, they prove this in heuristic P, and then they also use this kind of thing. And they show that at least at the level of Lie algebra representations in characteristic P, it's a kind of like, has an abelian nature. It's equivalent to coherent sheaves. So that's the localization part. And then there's kind of a small part that one has to go from here to here. A priori, they look quite different. This is a kind of completely discrete group. This is like a purely infinitesimal thingy. But somehow the point is that if I take representations of G, the reductive group, I already told you that all the irreducible representations here come by restriction from here. And you only see the ones from the box because outside of the fundamental box, the irreducibles are built by like tensoring and Frobenius twisting, and that Frobenius twisting is redundant on this subgroup. Similarly, you can differentiate representations like this. And when you Frobenius twist, the derivative will be kind of zero. So essentially, these two things look like they have similar kernels. And so one can actually match this up. So basically, the f of lambda, this is a complicated way of justifying that f of lambda, you just by hand map it to L of lambda here. And then this process should produce the correct sum.
Is it the functor?
It's not a functor, yeah, so it's there's actually some complicated like maneuvers hidden, completely hidden by the fact that I'm taking growth groups here. So everywhere I'm taking some kind of growth group.
If no other questions, let's thank the speaker.